Hello, guys. I am Naveenraj, and today I'm going to talk about a review of a research paper, the floating point error analysis of two-dimensional fast Fourier transform algorithms. And this review was also guided by Dr. Dhanabal R for the subject Computer Organization and Architecture. So basically, what is a floating point error? Floating point error mitigation is the minimization of errors caused by the fact that real numbers cannot, in general, be accurately represented in the fixed space. This floating point error cannot be eliminated. It can just be managed. Okay, so we're just gonna analyze the floating point error using FFTs, fast Fourier transform algorithms in two dimensions. So let's answer the questions and have a good knowledge about the research papers. Hmm. Talking about the first question, um, they've asked about the relation. The basically floating point is analyzed using the two-dimensional fast Fourier transforms. So, namely the conventional row column FFTs, which is RCFFT, row column Fourier fast Fourier transform, the vector radius FFT, FFT, VFFT, and the polynomial transform FFT. So these are the three FFTs used to analyze the floating point error. Okay. So they determine both analytically and in computer simulation also they can determine the errors. And computational comparison shows that VFFT and the polynomial transform FFT, even though computationally more efficient than the row RCFFT, they both show approximately the same results. VFT and RCFT is approximately the same, but in terms of computations, the number of operations is reduced. Uh, so VFFT is more better. And yeah, in the history, IEEE standard 754 established in 1985 as a uniform standard for floating point arithmetic. It is supported by all major CPUs. Before 1985, there were many syncretic formats. Okay, this is about why this paper was selected. Okay, just going to analyze using the fast Fourier transforms. That's all. So this is the existing architecture discussed in this paper, and I made this diagram using Photoshop. Uh, yeah, so this represents the RCFFT row, which is row column FFT, which is more efficient in analyzing the errors, analyzing the floating error. Okay, so and I have tabulated the results and graphs. So for n number of 4, 8, 16, 32, I've got theoretical experiment values, the theoretical and its experimental values. And based on that, we've got a plot. It's like a logarithmic plot, an exponential plot. It rapidly increases after a particular threshold. Maybe after this particular point, there's uh, there's change in the increasing step after this particular point. Yes. So this is the graph obtained through the tabulated results and results. And that's it about the third question. And the fourth question is the main part, that is the proposed architecture. So how is the architecture going to go? So there's x of n, which goes into a Fourier transform with x of n plus capital N by 2, and It approximately looks like a neural network. If you see, there are four values: x of n plus n by 4, plus n by 2, and 3 n by 4. So there are it's like 0.25 and zero point 0.5 and 0.75. These values are given, are put into the four different neurons in interchanging, combining each and every value, other values. Suppose x of n is there, and we take x of n plus 2, and we take a Fourier transform. X of n and x of n plus n by 4, and x of n plus 3n by 4, and we put it into this neuron, and we get some values: x of 4k, x of 4k plus 2, x of 4k plus 1, x of 4k plus 3. This is the architecture, and this architecture was drawn with draw.io tool, and Photoshop for the EPS formats. Suppose there's an input unit, and it goes to a DMUX and 8 points DFT unit, and multiply unit, transpose unit, and then the output unit. In between, the clock controller is attached to the input unit, and it ticks at every 10 milliseconds. And there's a sequence controller for the DMUX, so that the 8 points DFT unit is not influenced uh, lesser for the input from for the inputs from the input unit. And that's all about the block diagram. Now let's go to the transistor level internal diagrams. So what is a transistor level internal diagrams? They've just explained the operation. Shift operation is there, sticky operation, prenorm. There's a 1-bit shift operation. It can be a left shift or a right shift. And LZA correction, and rounding, normalization, and exception handling. This gives a basic idea of how the errors are analyzed. So experimental difference or swap. So with this, we get to know, okay, this is a closed path. This continuously happens. This is a closed path, and this is a far path. So the output of these two is given to a DMUX, and that gives, after rounding, and we get the Z value. That value we get. And yeah, that's all about the transistor level diagram. That doesn't have so much importance, but that's enough. And now we just see about the proposed architecture with existing architecture. There are number of slice registers. 69,000 slice registers available. 69,120 slice registers available. But we've just used 2,372, just 3.43% of the utilization. Similarly, we've just utilized 6.18% of the slice LUTs, and just 27% of the BRAMs. We just used 19, but the available is 68. It just shows the comparison of hardware resource usage of the proposed processor with the state of the R2456. Doesn't have so much of importance. Uh, that's just to know how much is not utilized, and we can utilize the other slice registers to improve the computation power and analyzation powers too. Now let's go to the seventh question, which is the advantage. So we already know fast Fourier transform helps us converting the time domain and frequency domain. The biggest advantage is that it can convert the discrete data into continuous data type available at various frequencies. So it doesn't mean that a frequency should be fixed at a particular level, particular range. It can be converted to any frequency. So we are rescaling it and then converting into a particular frequency. That is the main advantage of FFTs. And it also makes calculations easier as we deal with various frequency bands in the communication system. So it makes the calculations more easier. Talking about the advantages and disadvantages, we know it's global optimum, local optimum. So I'll talk about the advantages of the proposed thing, the proposed architecture. Parallelism is there, amenable to parallelism, low algorithm complexity, fewer iterations, handle multiple objectives. That is really important. Handling multiple objectives, backdoor ranking. But here the disadvantage is weights and objectives. Single objective. It can't perform multitasking and all. So it just has a single objective and it's limited parallelism. So comparatively, proposed architecture is more useful than the existing one, which means that is a slight improvement from the uh, existing devices or existing architecture, existing techniques. Uh, so let's see about the applications of the proposed design. Fourier transform helps to analyze the spectrum of the signals, helps in find the response of the LTA systems. So this is the main use of the Fourier transform. Okay. So even the discrete Fourier transform is helpful in digital signal processing for making convolution and many other signal manipulations. Yes. They find more use in DSPs for making convolution and in filters, DSPs and all. They're more useful. FFTs and FTs, that is Fourier transforms. So the Fourier transform doesn't have a full S plane. Okay, it just has the frequency J2 by F plane. They don't have the S plane. Instead of the S plane, they have J2 by F plane. And that's simple. Now let's talk about the flow chart. This is the last question. So let's start on one. Load one short fringe pattern. A fringe pattern is loaded. It's given to the fast Fourier transform. It's subjected to FFTs. And this isolates the first harmonic and shift it to the origin. We saw the shift here. As we saw, there was a shift here, one bit shift, the shift, sticky, pre-no operations and all we saw. So based on that, yeah, first harmonic and shift it to the origin. That's a after the pattern is undergoes the fast Fourier transform is shifted to the origin and inverse fast Fourier transform is obtained and we calculate the phase. Once the phase is calculated, we unwrap it and reconstruct the surface topology. So we get a particular signal. Okay. So this signal is subjected to a Gaussian filter. This smoothen out the this Gaussian filter usually smoothen out the what do you call mount heapy structures, unstable structures, and makes into a stable signal. This is mostly used in signal processing, DSPs, and image processing too. To make an image to make a noisy image look smoother, we use a Gaussian filter. So similarly, we use it here and this reconstructed surface topography is given to the Gaussian filter and after coming out from the Gaussian filter we reconstruct the rough surface profile. Okay, and we calculate the roughness parameters with RMS and RA. This is the complete block diagram or the flow chart. And this is the algorithm. There's a split up here. One signal of 16 points and two signals of 8 points, four signals of 4 points. It's just showing how the signals of look. And yes, talking about the research paper which I used, and this is the research paper which I have taken, and this is quite a mathematical paper, complicated paper, but it is more useful than the existing architectures. Yes, and that's all. We come to the end of the recording, and We saw about the particle transform used in floating point error analysis. And yes, thank you. That is the end of the recording. Thank you.